joining today's battery forum hosted by Volta. This session is focused on hidden insights, battery innovations with magnetic resonance. I am your moderator. My name is Jimmy Yuk. I head the strategic market development for Bruker BioSpin. And today, my friend and colleague here, Eduardo Nascimento, who is our solution product manager for our battery and polymer solutions. Now, I think to kind of start off the gate with everyone being in the room, maybe just to get to know a bit about each other and maybe some of the thoughts about that you guys had for batteries. I'm just going to launch this really quick 2-question poll just to get your insight about one, what area of the battery value chain are you closest to? Are you from academia, manufacturing, automotive, analytical, or investments? And really, when you think about battery, especially with today's sort of panel discussion, what are some of the biggest challenges you guys see in advancing battery technology today? Is it the performance? Is it the safety, manufacturing quality control, or maybe it's the supply chain and the materials sustainability? So give maybe 20 more seconds, and I can share some of the results. Okay, I think we have everyone answered. So here, share the results really quickly. So it's great. We have quite a bit of people here, 3 people here from manufacturing scale up, some in automotive, and 1 in analytical testing and standards. That's great. And then when it comes to biggest challenge, overall, love to see in the performance, so really understanding what areas to push the performance area, and also obviously the manufacturing and ensuring the quality of the batteries that are coming out. Interesting as well is the supply chain and material sustainability. I think that was also discussed in some of the panel discussion today. So great to see that. Okay, so really going to today's talk, I think one of the areas for you guys, if you guys don't know who Bruker is, Bruker, we are a global analytical instrumentation provider, really focused on driving innovation and helping many industries across for research and discovery and in areas of manufacturing quality control. We've been, really in the business for 60 years, partnering with a lot of industry experts, academia, driving really innovation at the forefront and building various tools where in sort of the landscape of Bruker, really areas from FTIR, from X-ray. Here today, we'd be talking about magnetic resonance to really dive and understand different modalities from atomic level, molecular, to even surface level, to really understand the various markets from pharmaceuticals, materials, foods, and today's topic about batteries. Now, one of the major drivers really for Bruker is the sustainable future. So building technologies for innovation when thinking about advancing human health and really understanding overall when you think about sustainability, but also to the products that we developed from the factories that we have, really going for carbon neutrality over the next 10 years. And then lastly, building this cooperative and inclusive culture. With that, we're going to go to the main topic today, which is our battery and understanding the hidden insights using magnetic resonance. And I will pass the ball to you, Eduardo, if you want to share your screen.
Okay.
Now, feel free to put the questions in that we will go through them as we go through the presentation. Thank you.
So can you see my screen?
Yes, we can.
Okay, so, and you see the presentation, right?
Yes, it looks great. It's on the presentation mode.
All right. So let me take this one out now. All right. So thank you all for being here today. So thank you, Jimmy, for doing the introduction. As I just mentioned in our speech, 30-second speech, I will be talking today about how magnetic resonance is driving battery innovations. So I will present how this magnetic resonance is being connected, not just with manufacturing, but also R&D. And I hope that we will also give a little bit of pause, right, Jimmy, in the middle. So we do some polls again, and then we discuss, and then we come back. So as Jan and Michael was saying, the idea here is that we interact, that we discuss. I think it's not just if you have questions, but comments and so on. So don't hesitate. We will have time to do both of them. All right. So let me see. Oh, wrong direction. Sorry about that. Right. So my first slide here, I can show you how the key trends in the battery value chain. So the battery market is a very interesting market, which has received a lot of investment in the past years and has a huge potential for the years to come as well. But the reason that I have placed this information here is because we see here on the left side that the cost of the lithium-ion batteries are still 70% related to the raw material. And then in this presentation, we will see how the magnetic resonance technique can support this area, because we can use it for the development of new raw material characterization as well, and even the battery cell electrochemistry. On the right side now, more related to the manufacturing side, we see that especially the ramp-up phase, that the scrap rate can reach peak numbers of 30%. And then, of course, the solutions that we have developed for this market can help a lot in improving this number for the manufacturing companies. So in this picture, I try to summarize how we have placed our technology in this market. So you see here on the left side in the product innovation that we have several techniques which are quite advanced. NMR and EPR can be very advanced methods. So this is somehow techniques that require some level of expertise for sure. So Bruker has been contributing to this area, not just with developing the hardware and software, but we have been connecting the battery cell companies to the research institutes, and Bruker itself is also partnering with many companies in this sense, so we can all work together in the development of new products. On the right side, you can see how we have placed our technologies in terms of manufacturing. So here we see the picture a little bit different, that we understand that in this environment, we are not expecting the user to have a deep knowledge about the technique. So we have developed here the so-called push button solutions, where the user will bring their sample to be analyzed to the instrument, and after some time, they are going to get a report with the results. So the main idea, we have selected here the areas that we see that we have the biggest potential to improve and to support this area, and I will be talking about these solutions here today. And actually, I will start talking about this side first. I will talk about the manufacturing applications or solutions that we have launched in the market, and I will start with the TD-NMR solution for the slurry analysis, because we know that mixing matters. So we know how important is the slurry in the production of the battery cell. Especially for the battery cells, which goes through the slurry process. Of course, we know there is a great potential for the dry coating process to take place here as well, where we also keep an eye on it for the development of new solutions. But so far, we see that most of the companies are still relying on the mixing for the electrode manufacturing. And then the homogeneity of the slurry plays a big role here, because this can affect the coating process and also the conducting performance. So I will demonstrate here how TD-NMR can help with that. But more than that, you will see that TD-NMR can also support, for example, recipe deviation. So if you have raw material origin deviation, something that you are not aware, and you are start doing your slurry mixing, and if you have some deviation, you can also detect that, and also in process variation. There is also TD-NMR is a very well-recognized technique in industry for many kind of applications that we have, and most of these applications are based on the calibration. So you can build a calibration in this instrument, and then you can correlate that to other properties of the sample. And I will show you some of these correlations that we have done, for example, especially for the solid content fraction determination in slurries. So here you see the basic principle that when you have a homogeneous dispersion, and this is where we have our optimized conductivity for uniform coating performance. And when we do this TD-NMR analysis, more specifically the relaxation time analysis, and do fitting algorithm to that, you are going to see this sharp peak, which represents the average relaxation time for this sample. And the principle is that as we move toward the inhomogeneous dispersion, that's that this peak is going to get broader and broader. And even in the extreme scenario here, you are going to see the appearance of a new peak in this relaxation time distribution graphic. And with this type of information, you can correlate or infer about non-optimal mixing specs. So if you are still in the ramp-up phase, still optimizing the specs of your mixer and so on, but if you are also monitoring the mixing of the slurry, because you produce a slurry in a batch mode, and now you are waiting for the next batch to be coated, so you can analyze to see if this is still valid. And even we had some great case here where we were analyzing anodes with silicon doped, and you can also see gas formation, so indicating that the mixing and the gas formation occurring at the same time. So you see here a quick example of a slurry sample that we received. We analyzed that in 3 different times, in the morning, afternoon, and another one at the end of the day. So you can see for the very first 2 measurements for the color blinded people, the blue and the orange spectra here are overlapped. But for the last one that was measured at the end of the day, this peak here starts to separate, and even the peak on the right starts to shift to the right position. And this is a clear indication that something was going on. So another way to analyze the same data is that you can transform that graphic in a number, like calculating the average T2, or even the distribution standard deviation. And again, you can see that for the very first 2 samples, the numbers are quite comparable, but for the last one, the sample was already demixed. So the second application that you have for TD-NMR in this area is for the recipe monitoring, as you said. And the principle here is that every time that a component of your slurry is changing, so the relaxation rate here will also change. So now we are not talking about how broad is this peak, but the position of this peak in this distribution graphic. And then this can support you as well in the development of new recipes, and even as I said, if you have in-process variation or problems with the origin of the raw materials that you are using. So here again is a quick example of 5 different slurry recipes. They have even solid content difference. And then, of course, if you try to analyze this graphical data, is becoming quite complicated, and this is where this numeric value comes to hand, is that you can see that all of them are all over the place. There was no intention here to have any correlation, just the idea is that if you have 5 different recipes, you will see 5 different numbers for that, because, and of course, if you are optimizing your process, you would like to see all of them to be at the same level. So the last application I will talk here, I said that you can correlate the TD and MR information with other parameters. For example, we normally correlate that with rheological properties like viscosity, shear behavior, and stability. And we have been using that to calculate the solid fraction content of slurries as well. So providing that you can calibrate the system and you need just 3 to 5 reference samples, you calibrate the system once, and then you don't need to do that anymore. Of course, unless you are changing recipes or working with different type of slurries and so on. But once you have a calibration curve, you can get your results quite fast. So for everything that I said, for all the homogeneity, for the recipe deviation, and for your slurry fraction calculation, this measurement time is something around 30 seconds, and you get all these results. So it's quite fast. Here you see an example of a sample that was a slurry sample that was diluted, and you can see that this correlates very well. The R squared here above 0.99, and you can actually see a nice example here how the mixing was happening for the samples that were diluted. All right, so now I will change topics. I will go to the other talk about the other solution that we have launched here, which is the electrolyte analysis using our benchtop NMR. So before we were talking about one technique, which is called time domain NMR. Now I will talk about FT-NMR, but based on a benchtop system. So here we know that the challenge when we talk about electrolyte, at least in my mind, the very first thing that comes to mind is the dry environment. That's because the electrolytes that we normally use in the lithium-ion battery, due to the presence of conducting salt like lithium PF6, they don't like water at all. So as soon as electrolyte is in contact with the minimal amount of water, it will start to degrade. And especially in the manufacturing sites, the main quality control methods that they use here is titration. They do the titration of HF and water. And then this titration method has several limitations. I think this is a method that we can still say that requires some skilled operator. It's not anyone that can do that. Maybe a good chemist can do that. I understand that, but you still rely on this ability, especially when we talk about the HF analysis, which is a non-selective method. And we have analyzed many samples where titration is actually titrating a new additive that you have in your electrolyte, or even because the titration is quantifying many other acidic protons that you have in your electrolyte and so on. So the method is not selective at all. So it can be time consuming if you consider all the calibrations and everything that you have to put in place to analyze the sample. From my personal point of view, I think the biggest limitation of this technique is the fact that it's a limited method, because you are only in the best case scenario quantifying or seeing water and HF. And when you have highly advanced methods like NMR, you can see a lot going on in terms of the degradation process. Okay, so what we have done here is that we have developed this workflow where you have an SOP basically explaining for the user what you have to do, which is preparing your sample, which is minimal. You bring that to the auto sampler or inside your instrument directly. You go to the software, you select your method, and after some time, you are going to get a report. So from here to there, you are not going to spend 2 minutes to do this process. And then after some time, depending on the number of components that you want to analyze, you are going to get a report. So what I will explain a little bit better about this process. So the method, I will start saying there is no sample preparation. Okay, the only thing that you need to do here actually is to introduce or add your electrolyte to the NMR tube. As I explained it, this is a push button operation. You go to the software, the method is already in place. You select this number. Our software nowadays, you can even deploy that in a touch screen monitor, so you can actually click on the method and that will start running. NMR per se is a highly reproducible method. I will show you some data at the end of this session presentation. This can accelerate the production workflow a lot. And we have also thought about how you can guarantee that the system is performing well. So we have some quality checks that is automatically included in the workflow routines. And then you can use, for example, this report to check the incoming goods, like when you receive your electrolyte from your electrolyte supplier, you check to see the quality. We saw that many times from companies that was saying, I will not do HF analysis in this electrolyte because we know that this is quite fresh. But then they open the bottle, they do the analysis, and they see a huge peak there. And then you cannot 100% rely on the quality of the electrolyte for many reasons. So with this method, you can do this um, sample identity check, or even when you talk about batch-to-batch identity. But I would say another big problem here, of course, is when you are doing the battery cell feeding. So you want to see if the electrolyte is in good health, so to say. So you can use the method, of course, to evaluate that. In this method, we have included three main groups or class of compounds here. So we have the HF analysis, as I mentioned before. You can see here in this example the HF peak. So that's why we say that with our method you are quite selective, because you are analyzing the HF peak. But we have also included the identification, automatic identification and quantification of carbonates and the lithium salt concentration. So supposing that we are talking to someone that is still in this R&D lab or battery cell chemistry lab, so if you are analyzing this right now, you are probably using three different methods: titration, gas chromatography, and ICP or HPLC. And with NMR, with our method, you can get all the results in 40 minutes. So it's quite fast, and it's a single method, and it's very easy to use. This is an example of the report. So this report is editable, so you can change the logos, change the colors, but more important, you can come here, for example, and change the unity of the method. You see, for example, that normally HF is reported as in ppm, lithium PF6 is reported in molar, and the carbonates is reported in grams per liter. So you can change to all 2 grams per liter if you want. So that's the idea. You can come here and make the report as you like. And then, of course, you can make this, for example, as a single page report. And then more important is that the report is available in multiple format, for example, in PDF, XML, and CSV, so that can be easily integrated to your LIMS system as well. This is an example of an electrolyte sample that was analyzed with our system. You can see here the typical carbonates, D, C, M, C, C. Of course, depending on the additive and the concentration of the additive that you are working with, you can also see the signal here. In the fluorine spectrum, you can see the HF, another additive here, the FEC, and you can see the lithium PF6 and some degradation compounds. So as I said in the beginning, here I am presenting some reproducibility results. So if you look in the column, we have here the same sample that was prepared in five different tubes. So you can see that for one system, the sample-to-sample variation is quite low, something around 0.5%. The same sample, if you prepare 4 samples and analyze that with 4 different instruments, so now we have a instrument to instrument variation, which can be in something around 1.23 to 1.9. So the overall variation here is estimated in 1.5%. So this is a quite reproducible method. So one of the main advantages of NMR is that the quantification here is done through external samples. So this is because NMR is considered to be an intrinsically quantitative method. So that when you see a signal in the NMR spectrum, that signal is proportional to the number of nuclei that you are analyzing. So using a reference sample, you can calculate that number as a reference. And then, for example, you can use water to calibrate your system, and then you can infer about the quantification of the other components. So different from chromatography, for example, where you need to have the same compound to build a calibration curve and so on. With NMR, you don't have that. So it's very easy, especially when you are talking about unknowns, where you are quantifying things that are not so easy to buy a reference sample for that. And then Bruker, if you buy the solution, the instrument from us, Bruker is also providing these quantification samples for you. You can see an example here of the report that is delivered after you do the calibration of the system. And remember, this calibration is done automatically. You leave the sample in the auto sampler, and the workflow will calibrate the instrument for you. So Jim, I think this is our break point here. So if we have, again, questions or about this application to manufacturing, I think we also have prepared some poll questions, right?
Yeah, thank you for that. We can do a second poll really quickly just to get everyone's sort of thoughts on the first half here. Let me just launch it right away. Just to get everyone's sort of feedback, are you familiar with nuclear magnetic resonance as a tool for battery manufacturing QC? So have you heard it quite a bit using your work? Maybe you've heard of the name, maybe you heard it in other industries, or maybe this is your first time hearing about NMR. And then the second part is, if you can unlock one insight about a battery, what would that be? Is it longer life, performance, safer, all about manufacturing consistency, or clear pathway for recycling and reuse? We'll give maybe 10 more seconds here. Okay. I'm going to end the poll here and I'll share the results. Great. It's good that everyone has heard about NMR, which is fantastic. So definitely as we go into the second half, we go into the R&D side of things, which really go into that second question about understanding about longer sort of that shelf, the cycle-like performance. How do we do consistent manufacturing? Really going down to the materials of the battery. So I think the second part here, Eduardo, definitely, I think a lot of people have, a lot of interest in. So with
All
that,
right.
let's continue.
Thank you, Jimmy. So, of course, when we start talking about R&D, we now talk about the key challenges that we see in the battery technology. So as Jim mentioned, higher storage capacity, safer batteries, and faster charging are always some of the interesting topics that we have here. So what we have in common here with these three areas is that solid state NMR, one of the methods that we provide with our instrument, can support this chemical understanding of batteries. And I will be talking about a little bit what we can do with with this technique. So solid state NMR is a very, so one thing here is that Bruker is also a provider of XRD, so X-ray instruments. And then X-ray instrument is coming to hand here, like it's very, X-ray and solid state NMR is very complementary. So this comparison that we do here is that all the things that you can do, for example, NMR, solid state NMR is sensitive to all battery components. So it doesn't matter if you are talking about cathode, electrolyte, or anode. So with solid or separator even, you can analyze that with solid state NMR. So NMR is sensitive to light elements, something that X-ray is not. So especially for lithium analysis, so NMR, solid state NMR is very unique in that sense. We can also analyze crystalline and amorphous samples, something that XRD cannot do. So NMR can provide structure and dynamic information, is very flexible and selective and non-destructive method. So we have basically two types of solid state NMR that we apply normally for the battery analysis, the so-called ex situ NMR. So here the idea is that you create your batteries, or even you start analyzing your raw material. But the other point is that you create your battery cell, you do your cyclings, and then you open your battery cell and extract or put all the components that you want to analyze in this rotor, and then you do the analysis. The other part is the operando NMR, where you create your battery cell inside the NMR probe, and then you bring that to the NMR instrument and you do your cycling and NMR in real time. So how we can use solid-state NMR to characterize battery materials. So we are going to start talking a little bit about this higher storage capacity. So here we have a nice example where XRD and NMR was applied to study the structural evolution of sodium in cathode material. So with XRD, you can have you can identify this long range order and even track this global phase transition during cycling. And with NMR, we can basically talk about the preferential site occupancy. So in this study specifically here, the authors were able to see that in the higher state of charging, for example, that the sodium was preferably sitting on these octahedral sites of the OP4 phase. And then more than that, after discharging, that this process was reversible and the sodium coming back to the P2 phase. Bruker recently launched a new version of the solid-state NMR system, the so-called 200 megahertz. So normally in NMR, we are looking for higher fields. Bruker launched a lower field instrument. That's because for analyzing paramagnetic substances, the lower fields are more important because then you can decrease the interference. You can see here, for example, that when you go from 400 megahertz to 200 megahertz, the signal is more clear. So you can easily study the structural evolution of the paramagnetics, ion dynamics, and for operando studies as well. So now going quickly to the safer batteries, I see that our time is running fast. I will try to speed up. So here an example of the operando NMR. So now remember you have your cell inside the NMR probe. So this is a spectrum of your whole battery cell. So in the beginning, before the cycling, you can only see the electrolyte signal here because we are focusing on this lithium analysis. So in this window of analysis, so you don't see any lithium metal here in this region. And then we applied some cycling, some charging to this battery. And then after some time, you are going to see the lithium metal being deposited here in the collector, but also in the SCI phase. And then after some time, you see the formation of that lithium and over time, the accumulation of that lithium in your battery cell. And then monitoring that lesion growth, you can calculate the capacity loss due to that lesion, but also the capacity loss due to the SCI formation. You can use that to compare different electrolytes, for example. This is an example of our recently launched probe. So in this case, this company, which is a Bruker partner, which manufactures the operando probes, has launched an option to work with the coin cell batteries. And you see an example here of an NMC graphite battery cell being analyzed with this probe. So faster charging. So here we will see how the ion mobility and dynamics can support this very important topic. So nuclear magnetic resonance is uniquely sensitive to local atomic and electronic environments, and diffusion NMR and relaxation NMR can provide a direct insight in this ion mobility and dynamics. And there are so many applications that you can do with that. Quality control of electrolytes as well, formulation of new electrolytes, or even formulation of new battery interface for the solid state batteries, for example. So here is just an example of diffusion studies where, for example, when you vary the temperature of the sample and calculate the diffusion, you can actually calculate the activation energy, which is the minimum energy required to move the ion in the battery. So you can do that using NMR, and this can also influence the ion mobility. So diffusion experiments now where you change the diffusion time, you can calculate here the electrical conductivity, which are both important informations when we are talking about developing fast charging batteries. Another example here, now using the relaxation times instead of the diffusion, talking about ion hopping and again, calculating activation energy, just a different way of doing that, but can be used to infer information about new cathode materials, for example. Quickly, EPR is a very similar technique as NMR. So in this case, we are not monitoring the nuclei, but the electron, the unpaired electron in your substance, and this can be used for detecting degradation in electrode material, but also oxidation of electrolyte components, parasitic reactions, and structure characterization of electrodes. So here I show only one application, which is very nice, where you can monitor anode material after cycling, because the APR signal, the shape of the signal can tell you about the state of the lithium, if it's bulk lithium, mossy lithium, and dendritic lithium. So after some cycling, you can actually evaluate if you have some dendritic lithium formation. Last slide. I think I'm quite on time. So I invite you to visit our battery web page. So you will find a lot of dedicated material to the batteries here, but also application notes and webinars. Especially for the research instruments that we have. If you want to have a demo, please contact us. And as I said in the beginning, Bruker and Jimmy is heading this department at Bruker for the strategic collaboration here. So if you are looking for a collaboration, don't hesitate to contact us. And with that, I say thank you. I will keep this screen here if you want to see the content, but if you want, my email is eduardo.nascimento@bruker.com. And thank you for your time.
Thank you, Eduardo. No, this is great. And obviously, feel free to email us if you want a copy of the slides as well. We can definitely share that. To end it off, just wanted to launch the last poll here, um, really on just your thought overall from learning about NMR for manufacturing for batteries and for R&D. Where do you think, from what you've seen, what Eduardo presented, to really understand, for batteries, it degradation mechanisms? Was it the real-time operando measurements that seemed very interesting? Was it more for the quality control, like the electrolytes and the slurry? Or maybe some of the sustainability, because being able to optimize these components will really help in creating a more sustainable battery. And the last part here is, what do you think the largest barrier to NMR? Is that the cost, lack of in-house expertise, limited throughput, or the lack of awareness of the applications? So give maybe 10 more seconds here. I think most people have already answered here. Share the results here really quickly. Thank you for putting your answers. A lot of it is on the degradation mechanisms, one for quality control, and really the cost of instrumentation, lack of in-house expertise, and the awareness of the applications, which is good. Hopefully for that person there, now you learn a little bit more about NMR. I know we already hit some time, but definitely wanted to really quickly open up if there's anyone that has like a specific question with Eduardo here to ask about some of the things he presented today. So if you want to maybe unmute, feel free to maybe ask me your questions right now.
Oh, question.
Yes, Alan.
Yeah. How competitive is this technique compared to other techniques used for study of the degradation, the mechanisms, and the others in batteries?
Okay. I think, of course, being this business of analytical methods, I would say, of course, NMR has its unique information. I think the main advantage of NMR in general, as I mentioned, is that when you are talking about quantitative analysis, the calibration of the instrument is very easy, so that can help you a lot. But when it comes to degradation compounds, for example, or even the mechanisms of degradation, is that you can have this picture all at once, so you can see this happening in real time. I prefer to see what are the main advantages of NMR in that sense. I mean, of course, Bruker is a company that is providing X-ray, mass spec, Raman. So there are many unique applications for each of these technologies in the battery market. NMR, I would say, is the repeatability, easy calibration, easy level of automation. So everything I mentioned before for the manufacturing side is automated. So the level of automation of this method is quite high. And then the level of information is also very unique. So I would position my area, magnetic resonance, in that way. I think actually it was part of the question, and I saw that someone answered that the cost of the instruments can be relatively high. This is true, especially when we consider the high-tech instruments that we use for R&D. But for the manufacturing solutions that we have developed, we are talking about this benchtop systems. So those were systems that were developed to be low cost, low footprinting, and low maintenance. Like the benchtop NMR, you don't need to worry about cryogenics, for example. This is a permanent magnet, and the cost of the instrument is considerably lower when you compare to a standing floor instrument, for example.
Thank you. For me, it's very
Thank you.
new. The user of the NMR for characterization the battery
Sure.
is very
Don't
interesting indeed.
Sure. You have our contact, Alain. Don't hesitate to contact us if you want to learn more. I would love to connect with
Sure,
you
sure,
later, and
sure.
then we show you more. I know we are not so close, but maybe close enough. If you stop by Germany anytime, you can
Yeah,
come
yeah.
and visit our labs as well and see how this work in practice.
Thank you, thank you, thank you so much, Eduardo and Jimmy.
Thank you as
Thank
well.
you.
Any other questions? Feel free to unmute or type your questions in the chat. If not, then maybe I know we're already a bit past time. So wanted to again thank you everyone for joining our session. Again, if you would like a copy of the slides, feel free to email the email here or at my email, jimmy.uke@bruker.com. Thank you again. Love to participate in future forums. Hopefully, if there's any topics that are interesting, more in the analytical space, again, let us know. Would love to bring some of our experts to continue to engage with the community here. So thank you all. Hope you guys all have a great rest of your day, and we will talk again soon. Thank you, everybody.